2026 renewal of the Biomedical Engineering Senior Design Expo and Competition. We acknowledge and appreciate the presence of faculty, families, alumni, and honored guests who are here with us, as well as those who've joined us on platforms such as Facebook Live and on Zoom. My name is Michael Christie, Associate Teaching Professor, Primary Instructor for Senior Design. I'd like to, before we move on, I'd like to introduce you to our undergraduate program director, Dr. Anthony McGord, who will give a few words of welcome. Dr. McGord, let's give it up.
All right, thank you, Dr. Christie. Appreciate everybody coming. As you all know, this is the capstone of the undergraduate program. Every engineering program requires that students do a comprehensive design which incorporates everything that they've learned throughout their 4+ years in the program. And this, of course, is what allows you to demonstrate your expertise and knowledge as an engineer and move on to the next phase of your career. I welcome, of course, all the students and the judges. We really appreciate you guys being here. Your role in this is extremely important to us because as part of our assessment program, we require or utilize outside expertise to help us evaluate what our students are doing and what they're producing and what kind of job we've done preparing them as engineers. I appreciate any visitors that we have. It looks like all we have is students that are, usually we have a lot more visitors here. Hopefully we have some other students that are going to be following you guys over the next couple years into this course. Hopefully we see them come so that they can see what you're doing and get a good idea of what is prepared for them. So we can get on with our activities today. I'll turn it back over to Dr. Christie, and I hope you guys enjoy this time, because even though I'm sure it's very stressful leading up to your presentation and giving your presentation, but hopefully you take advantage of the next couple of days as a celebration really of what you accomplished, and which obviously this is just the last phase of this, or the last step of this phase, and the beginning of a new and exciting phase for the rest of your career.
Thank you, Dr. McGorn. The Senior Design Showcase and Competition is really the culmination of a year-long study. We're in the first semester under the direction of Professor Shahristani. He's over there. Give it up. Students are taught the rudiments of medical device product design, development, manufacturing, and planning. In addition, students form teams and engage the medical device industry and allied industries, locally, nationally, and even internationally, to identify and secure sponsorships for projects that address unmet biomedical needs. The first semester ends with the students presenting their project proposals before a panel of biomedical engineering faculty who challenge their technical decision-making and evaluate the scope and feasibility of each project. We're very grateful to have the sponsors. I'm happy to report that we have a number of our repeat sponsors and also new sponsors. Can you give a shout out to our sponsors? Thank you very much. In the second semester, this is where learning is done by doing. And students, upon approval from the first semester, begin to work on their prototypes, refine their designs. They go through manufacturing. They go through design thinking as part of their education. Certainly QA aspects, verification, etc. And on top of that, students are provided with at least one lecture to assist them in terms of professional development. Let's get started with all of this, but first I'd like to introduce the judges, and then let's do a little bit of housekeeping. To my right and your left is Ms. Celeste Randolph. Give it up. From Thermo Fisher Scientific, EHS specialist. To her right is Ms. Maria Anderi. Let's give it up for Maria. Systems engineer from Abbott Labs, diabetes care. Then Kelly Rojas. Give it up for Kelly. Research supervisor in the Media and Innovation Lab at University of Miami Healthcare System. To her right is Dr. Rashmi Banjari. Give it up. She's a postdoctoral fellow at the FIU Electronics Packaging Lab. To her right is Mr. Ahmed Assad. Let's give it up for Mr. Assad. Manufacturing engineer from Stryker. Later on, I'll tell you all of the wonderful stories because I was anointed as the historian for senior design. Let's do a little bit of housekeeping. Here's programs are outside, but you can. There are also programs online. You can take a look. There are 8 teams. We will go through the presentations. There'll be a changeover, yes, and thereafter there will be the junior design poster competition. Yes, there's a junior design poster competition, and that will take place almost immediately after the senior design presentations. During the intermission, judges will retreat to the BME conference room for deliberations. Yes, it's a closed door affair. And thereafter, we will reconvene here at 2 p.m. For the awards ceremony. Yes? Rules of the competition. Teams are given 10 to 12 minutes of time to do their presentations. And at the 11th minute, they will be given an alert. And then at the 12th minute, there will be a second alert, which will inform students that they have another 30 seconds to wrap up their presentations. So let's get started. To the stage, team number 1. Team number 1. Team number 1, Cervexa, novel medical device for early risk assessment of preterm labor. Faculty mentor, Dr. Anamika Prasad. Alumni mentor, Ms. Chelsea Jai Prasad. And this project was sponsored by Polarimed, Optics and Imaging. Let's give it up for team number 1. Rachel Valdez, Andres Garcia, Natalie Telachia, and Nesta Benepata. Sorry, Nesta.
Please wait, the judge, timer.
And who wants to, somebody needs to tell them when to go.
It's at 12 minutes. Yeah. Here, 111, first alert. We'll get you the better minutes.
Good morning, everyone. I'm Rachel, and these are my teammates Andres, Nesta, and Natalie, and we are Team 1. Today, we will be presenting our senior design project, Cervexa, a novel medical device for early risk assessment of preterm labor, sponsored by Dr. Amela through Polarimed. So a bit of background, this is the anatomy of the cervix. The uterus where the fetus is located, the vaginal canal, and the cervix between the two. It is important that throughout pregnancy, the cervix remains firm and close to retain the fetus as it develops. Highlighted in green here, you can see our 4 testing sites. And so as pregnancy progresses and as you get closer and closer to delivery, the cervix undergoes a process called effacement, where softening occurs and it shortens. Now, if this process occurs too early, it can lead to a spontaneous preterm birth. Now, what is preterm birth? It is birth before 37 weeks of pregnancy. Some risk factors are being an over or underweight mother, history of preterm birth, or infections. The impact that it can have are serious cognitive and cardiovascular impairments, requiring intensive care, as can be seen here, where the baby is connected to tubing and machines, fighting to breathe and grow. So preterm birth is a major global health issue. It is the #1 cause of death in newborn infants, with about 13.4 million babies born globally preterm, making it 10.4% of all births, emphasizing the need for more global awareness and preventative measures. Preterm birth is most prevalent in low-income populations, as can be seen here, where there is limited access to care, and the current diagnostic methods are subjective, expensive, or inaccessible, creating disparities in assessment and treatment through global perspective. This highlights the need for earlier, more accessible, and more accurate technologies. Survexa addresses this gap by enabling providers to assess preterm labor risk overall, preventing it through global engagement. Now onto the current modalities. So the first one that I'll be discussing is the finger measurement method, in which the provider would insert their fingers into the cervix. So the more dilated that the cervix is, the higher the risk is of preterm birth. Next, the transvaginal ultrasound, in which the provider would measure the length of the cervix. The shorter the length of the cervix, the higher the risk is of preterm birth. However, cervical length changes occur after cervical stiffness changes. And lastly, the disposable cervical aspirator that measures cervical stiffness. A lower cervical stiffness is correlated to a higher risk of preterm birth. However, this method is only available to providers in Switzerland and Germany. Overall, our project scope is to deliver a functional prototype that measures cervical stiffness with high precision. Our project was completed in April of 2026 within a $5,000 budget. Now that I've addressed the foundation of our project, Andres will present our clinical and business needs.
So there's a strong clinical and business need and backing for this project. As you can see, as Rachel said, 10.4% of births from 2022 to 2024 were preterm. 78% of these were spontaneous preterm births, making this the #1 cause of death in newborn babies. This represents a strong need for a device and a tool that can assess preterm risk early and more objectively. In this business side of things, there's a 7% potential market increase from 2025 to 2034. And with market spending worldwide of $15 billion, this device could generate $140,000 to $350,000 in first-year revenue and save the hospitals $10,000 to $30,000 per case. So our proposed solution is Survexa, a handheld biomedical device that is used to assess the patient's risk of undergoing preterm labor. It uses a negative pressure response and provides real-time pressure response, which makes our device reusable, and then our device is reusable, portable, and a cost-effective solution to the current modality. Next, I will pass it on to Nessa, who will be speaking on the market requirements and design inputs.
Thank you, Andres. So for our market requirements and design inputs, we focused on making our device both reliable and easy to use in a clinical setting. So some of the key requirements that we identified for our device was that it must be able to precisely measure the cervical stiffness with pressure readings up to 40 kPa. It also must be able to run for at least 45 minutes without degradation and give a stable reading within 15 seconds of operation. Some of the other factors that we also looked at were sterilization, ergonomics, and continuous running during different conditions. Now I'm going to pass on to Natalie to talk about the design progression.
Thank you, Nesta. So you can see here some of our earliest design concepts, including our early probe and grip design concepts on top, as well as the pistol grip design we settled on the bottom. This grip is common in high-power, high-precision applications such as drills and handguns. We also settled on a simplified probe design you can see here. Now we will discuss the development and rationale of our final design. Here, you can see that final design in a 3D model turnaround view. First, we will discuss the grip. The grip houses most of the electrical components, including the pressure sensor, the battery that powers the device, and the microcontroller. It splits in half in order to be able to access these components for manufacturing and servicing. The shape is elliptical. We determined that this would be the most comfortable for the provider to hold. Other features include vents for heat dissipation of the battery and a charging port. Now we will discuss the body. The body also houses some electrical components, including the display, the pump for pressure generation, and the power switch. It also splits in half like the grip in order to be able to access its internal components. A flexible tubing runs from the pump to the probe, and from the probe down to the pressure sensor below. The display is mounted at an angle so that you can read it easily, and here you can see a hollowed out internal view of our device. Next, I will discuss the probe. The probe is the most critical part of the device, so I'll take a moment to explain how it works. The tissue would be here, and the probe is placed on the tissue. The pump generates suction through the suction channel you see here. And as the pump generates suction, the tissue is displaced a 4 millimeter distance from the front of the probe chamber to the front of the suction channel lip. Now, meanwhile, the pressure sensor is sensing the changing pressure in the chamber through the bottom channel. Once the tissue is displaced the 4 millimeter distance, the pressure will stabilize, allowing you to take the reading. This pressure that's needed to reach a stable pressure reading depends on the stiffness of the tissue. And here, you can see an exploded view showing all of the internal components of our device. Now I will discuss the simulation results. We performed finite element simulation in COMSOL multiphysics to determine the pressure that would be needed for a 4 millimeter displacement of tissue. So you can see in the color bars here, they indicate the displacement per unit pressure on an axisymmetric model of the cervix. So the center here is the center of the aspirated portion shown in green. We determined the displacement per unit pressure D that would be needed for we determined the displacement per unit pressure D in order to determine from the formula the pressure P that would be needed for displacement of Y. In this case, Y is 4 millimeters. We did these simulations and got the results of the calculations for each stage of pregnancy using literature values of stiffness, and the results are shown here. Finally, our static simulation showing that the device can handle the normal stresses of operation. Now, I will pass it on to Andres to discuss the electrical components and manufacturing.
Thank you, Natalie. These are all our electrical components. They're tied together with the electrical diagram that you see on the screen there. For our manufacturing, for the body and grip components of the device, we use additive manufacturing process using a bamboo 3D printer. The material we decided to use was PETG. It provided a stronger, more durable, and better ease in prototyping for our device. Next, we use tap screwing to screw the grip and the body along together. The probe, we originally planned on using CNC milling to make our device reusable. But due to many constraints, we had to go into a fast and rapid prototyping approach, so we decided to use a PETG probe that still shows the functionality and structural stability of our device. In clinical settings, we would normally use a medical-grade stainless steel probe that would make the device reusable and sterilizable with the ethylene oxide sterilization processes that are normally used in hospitals. Next, I will pass it on to Nesta, who will be speaking on the verification test.
Thank you, Andres. To verify that our device met the design requirements, we conducted several key tests. The first one is the pressure sensor precision test. This is also our killer test. So what we did in this test was we placed the probe on top of the phantoms that you see on the table and collected the pressure readings accurately. So what we found out was that the device was able to give a less than 1% of variation between each of the trials of the separate phantoms, and it also gave us a p-value of less than 0.05, indicating that our results were statistically accurate. Moving on, we did the battery lifetime test, where we let the device run continuously until depletion and recorded the operation time. Our device showed that it had sufficient battery life and was able to run exceeding the 45 minutes that was the minimum that we set, and gave us an R-square value of over 0.9, indicating that the device ran continuously without degradation. Moving on to our last test, which was the response time test, where we measured how long it took for the device to stabilize the pressure readings. As we can see in the graph, the device was able to continuously stabilize within 15 seconds, indicating that the device was able to provide fast and reliable feedback. Here is the list of the other tests that we conducted. We had 6 other critical tests, and all of them passed. So coming to our cost analysis, our total budget was $5,000, and we were able to complete the project within the promised budget, and our total unit cost was estimated to be around $440. Coming to our regulatory assessment, we classified our device as a Class 2 device, as it poses moderate risk and does not need clinical trials as of now. And the regulatory pathway we chose was the 510K, as there's a predicate device that exists as of now. The other ones were not chosen as they did not fit the criteria for our device. Moving on, here is a list of all of the engineering standards that we deemed fit for our device. And now I'm going to pass it on to Andres to talk about the future work.
So for our future work, the first thing that we would do is actually create the CNC milled medical grade stainless steel 316L probe. This would then be used in clinical draws to using our device to obtain cervical stiffness range values. This would give us a basis for and give us real patient data. Next would be a reduction of noise, a suppression of noise. So that they would be used for patient comfort and then providing different grip diameters of the grip for the patient of the clinician. So we would like to acknowledge Dr. Romella as our sponsor, Professor Sherstani and Dr. Christie for their help and guidance along with this project, and our alumni and faculty mentors, Dr. Prasad and Sosi Jagprasad. Thank you for allowing us the chance to present Cervex to you and the work this team has done for you. We will now take any questions.
Thank you so much for the presentation, very nice. Took a look at the device.
Yes.
I just wanted to know how is it being usable? How
So-
do you change the?
So the probe would be, do you want me to get the mic? So the probe would be, would normally be a medical grade stainless steel 316L probe. And in most hospitals, they have the ethylene oxide sterilization process. So we tested this in one of the verification tests we used. We put metal into one of the sterilization processes that we had access to, in which it passed and it was sterilizable, and that is the regular practice that they use in most gynecology offices. Any more questions?
So you're measuring the negative pressure, so how does it relate to cervical stiffness?
Answer that. Thank you. So as I said previously when I was explaining the probe, so the displacement or the pressure that's required for a consistent displacement, like the displacement is held constant, so what's changing is the pressure needed to displace the tissue. That pressure is going to depend on how stiff the tissue is, so like if the tissue is really soft, for example, it's going to require less pressure to deform it. So that's how we correlate that negative pressure that's required into the cervical stiffness value.
Just wondering, what was the driving factors for the length of the device, the handle, and also the length of the handle?
So for the grip and the body, the main thing that we use for the grip, realistically, we use research processes and we use what is the most comfortable hand measurements in gun sizes. We calculated the angle for the grip and the body to be the most accurate hand measurement for clinician comfort. That's what we did for the grip. Then the body, we use it to be able to basically house all the rest of the components that go on the top, which would be the display and the pump, and as well as the pressure sensor that will go in the kind of between the body and the grip. And then for the probe, the length that we used is longer than the longest length at the recorded for the vaginal canal.
In order to also get more data onto the length that we should use for the probe, we compared it to the lengths that they usually use for pap smears, because doctors are more used to that length. In order for them to be more comfortable with a length like this one, we used that length, which was about 7 inches. So that's the length that we decided to use, the average length of the pap smear devices.
Okay. Let's give it up for team number 1. Judges, you have a few minutes to gather your notes, and in the meantime, I'd like to call team number 2 to the stage. Team number 2. Dual action microsurgical clip applicator for improving precision in vascular procedures. Sponsored by KLS Martin LP, faculty mentor Dr. Anthony McGorn, alumni mentor Mr. Nicholas Latone, team members Ms. Destiny Nance, who's a project manager. By the way, if you're looking at your booklets, the name of the asterisk is the project manager for the team. Fabian Lopez, Jeff Charles, and Michael Wortham. Close enough? All right, thank you very much. Thank Please have your attention. Thank you, Professor McGorn. Joining us, our sixth judge, very important, is Ms. Paula Lugo. And you see the smile on my face, welcoming Paula and the rest of the team back. She's a senior staff manufacturing engineer at Stryker. So Stryker is represented, 33% in the house. Couldn't help but doing the numbers. Paula, welcome. Let's give it up for Ms. Paula Lugo. Thank you for taking the time to join us.
Thank you very much.
Tell them when to go. That's fine.
Good morning. We're team 2 on our project is a dual action microsurgical clip applicator. We work on our sponsor, KLS Martin. My name is Savion Lopez. I'm the clinical lead.
My name is Destiny. I'm the project manager.
My name is Michael, I was verification lead.
So vessel ligation is a fundamental part of surgery. In craniomaxillofacial surgery, or CMF surgery, vessels can vary from 0.5 to 4 millimeters in diameter. Currently, microsurgical clip applicators are single clip applicators. So there is a clear need for a compact dual action microsurgical clip applicator capable of delivering clips with controlled spacing, high positional accuracy, and controlled deployment forces. So current modalities have areas where they could improve, mostly with clip spacing and having to repeatedly handle fragile tissue. Some advanced clip appliers try to introduce this kind of stuff. However, they tend to be very costly, very bulky, and not really usable when it comes to the microsurgical aspect. Right now, there's no commercially available system that allows surgeons to set the spacing and deploy 2 clips at the same time through a single ergonomic interface. This sort of thing can increase over time, can increase the risk of endothelial trauma, and also it leaves most of the actual placing to the skill of the surgeon, which that affects how reproducible the actual surgery and the results are. Now on to,
Fabian. So what were the most important market requirements that we needed to satisfy? First, we were tasked with designing a device that would allow for the inclusion of small caliber blood vessels. These are blood vessels between 0.5 to 4 millimeters in diameter, through the simultaneous placement of 2 vessel clips. This was our most critical design requirement because vessel clips are often or always used in pairs, often 2 to 3 pairs per occlusion with multiple occlusions per procedure. And as we also stated before, the current modality of applying vessel clips, whether that be manually or using a vessel clip applying instrument, only allows for the application of vessel clips one after the other. Our second requirement involved surgeons. Surgeons have specific spacing requirements for placing these vessel clips between 5 and 10 millimeters apart. We were tasked with incorporating this vessel clip placing within our device from the very beginning. This would prevent the adverse post-surgical outcomes that come with misaligned vessel clip placements. So we translated these into our design inputs. We decided to design a device that would have a jaw with the proper clearance to fit 2 vessel clips and allow the vessel clips to be placed between 5 and 10 millimeters apart with 1 millimeter intervals in between. We also decided to create the jaw with proper clearance so that when the clips are placed, they won't snag on the clips, needing a 10 millimeter clearance in order for that to happen. We also designed the device so that 50 units of force would be sufficient for applying the clips, since this is the force needed to both actuate the clips and apply them to the vessels. So we moved on to our first design concept. In this design concept, we have the jaw here with the proper clearance for 2 clips at the furthest distance of 10 millimeters apart. However, this design was too bulky, and it also, at the jaw interface, it allowed for fluid ingress into the device, which could impair function. To combat these issues with the first design concept, we decided to slim down the body of our device and increase the size of the jaw in order to prevent fluid ingress into the device. However, this increased jaw size did cause impairment in the field of view of the surgeon. To combat this in total, we completely shrunk down the size of our device. However, this caused the internal mechanical components in our device to be so small and precise that it increased the manufacturing cost, which was something that we were very cautious of during our design process. This led us to our MVP design. We decided to go with the scissor-like surgical design. This is a design that surgeons are very familiar with for our dual vessel clip applicator in order to grab and place two vessel clips simultaneously onto the vessel. We also finalized the design of what we call a clip cradle. This is the precision component that would allow for the proper alignment, consistent and accurate placement of the vessel clips onto the vessel at the proper millimeters that the surgeon requires it to be placed at. Here's the engineering drawing of our dual vessel clip applicator, as you can see. And as for manufacturing, so since our dual vessel clip applicator would be in contact with bodily fluid and tissues, we decided to go with the titanium grade 5 material for this device. This is because it has this is because of its excellent biocompatibility, its excellent wear resistance, its low ion release to prevent the ion release into the body, as well as this high strength to weight ratio, allowing our device to be a very lightweight, however, reliably strong device in order to properly apply the forces needed to actuate the vessel clips. We decided that our clip cradle, since it wouldn't be in contact with patients, would be made of an acetyl POM-H polymer. This was a sufficient polymer because it has excellent wear resistance with a very smooth finish, preventing the introduction of particulates into the body when clip transference is happening, as well as consistent manufacturability, making it a very cost-effective material while not compromising on precision needed to have these vessel clips placed at the proper distances apart. I'll now move on to our engineering analysis with Destiny.
Thank you so much, Jeff. So the first analysis that we performed was a motion analysis. So we applied a motor at the pivot where our device moves, and we looked at a 50 Newton force at the jaws to simulate the force that the clips enact on the jaws as the jaws attempt to open the clips. With that, we were able to get an approximate moment at the jaws of 4.6, and we were able to use that to work backwards to get a value that the user would actually be using the force to actually open the clips at 15 Newton. So the point of this was to ensure that the force that the user is using is actually reasonable and could be repeatable in a surgery, since again, market requirements go back to increasing efficiency in the surgery and decreasing the time it takes. We don't want to increase surgeon fatigue with that. Additionally, we performed a static analysis on the jaws. So again, we had that 50 Newton force, so it's going acting on both ends to ensure that our jaws would not fracture or break given the force that is needed to open the clips. With that, we had a max stress of 124 megapascals, which we saw again under the yield strength of titanium, which is a nice factor of safety and reassurance that our jaw will not break. Additionally, we performed a static analysis on the handle of our device. So we treated it as if it were a beam and applied 100 Newton force at the end there. So the 100 Newtons, we were kind of visualizing as if someone were to squeeze our device as hard as they possibly can. Would it still break given the bending that is applied? And we see here that it does not. Our max stress at 630 megapascals is again still under that yield strength for titanium, giving a significant factor of safety considering that the user input force would be well below 100 Newtons. And so again, this gives us reassurance that our device is reliable. With that, I'm going to pass it on to Michael for verification.
Thank you, Destiny. So as per 3 of the critical verification protocols we completed, we wanted to ensure that the spacing was accurate and controlled when being combined with the cradle and the use of our dual applicator. Additionally, we wanted to verify that the dual applicator actually reduces the time it takes to place the clips accurately onto the vessel. So as for the accuracy trial, we did 10 trials per measurement. So we did one for each of the spaces in the cradle, and we did one with a single applicator as well. And we did it with just the dual applicator, and we verified that all of the placements were within a 0.1 millimeter tolerance. So that verification trial was passed. Additionally, we measured the time it took to place with the dual clips versus the time it took to place with a single clip applicator. And we noticed that it was statistically much faster to do the dual application across all of the different spacings, noticing that they actually got faster as of course this was done all by a single subject of that testing was actually done much faster as the subject became more familiar with the device. As for the precision comparison, we verified that the use of the dual applicator means that the spacing is more controlled and consistent across all placements, and eliminates the uncertainty that comes with using a single clip applicator. As for the novelty of our device, as I just mentioned, it eliminates the need for sequential placement, and it also eliminates the need for surgeons to guess or to estimate how far apart the clips should be when doing a certain procedure. As for how we address the global learning requirements, our device is very simple, and this helps with the awareness global learning target. We consider that surgeons need to use this device in all kinds of different environments, and we need to make it simple to manufacture. Additionally, as to mention the engagement, the development of a clinically relevant, scalable solution for improved surgical efficiency is something that we were required to contend with, and we feel that our design reached this goal. As for the engineering standards, I'd just like to mention the most important ones we have. For the material mechanical ones, we ensured that the titanium grade 5 met the surgical grade yield when doing these procedures. Additionally, we had the mechanical standard that validated the shear strength and fit of the pivot screw of our design. As for future work, due to the constrained nature of our timeline, we weren't able to add everything that we wanted to. We would like to add a locking mechanism in the future if given the opportunity. We feel this will help with the ergonomics of the device. Additionally, we would have liked to continue with sterilization and biocompatibility protocols verification. We included our references, and we'd like to thank the BME department, Dr. Christie, Dr. McGuire, and our sponsor, Kayla Martin, for assisting us with this project. Yeah, any questions?
Alright, so Chelsea, I did have a question. As far as current surgery and the surgeons inserting one clip at a time, it does allow them to rely on their expertise into where they're inserting. So how does this dual application, I guess, in terms outweigh that knowledge they would rely on?
Much. It's a very good question. So essentially we were looking at why we wanted to do 2 clips instead of 1. We were looking at decreasing the time it takes to do the surgery, and therefore like saving the hospital money, saving the surgeon's time. Obviously surgeon expertise is definitely something that we have to combat, and that is why, again, you know, in the future, like we have the different spacings now, but we would have definitely liked to include a lot of like different spacing so that the surgeons are able to do that in a more precise manner. Nothing against their expertise, but we did see that when using our cradle, there is more precise in that measurement, and we do see that there is value in having those precise measurements compared to using single clip applicator and sort of guesstimating.
To add on to what she said, on top of precision, consistency and accuracy are the biggest issues when it comes to adverse post-surgical outcomes. So because our applicator allows for the clips to be aligned specifically at the interval that the surgeon needs it at, and they can consistently rely on that through our device, that would be something that we would prevent with these post-surgical outcomes. It would be the misaligned clips, the clips moving, or being placed in regions where the spacing was just a little off, which caused the either tissue tear or vessel tear.
And also to keep in mind that clips are usually placed in pairs or 3 at a time. It's very rarely that they only place 1 clip. So they would have to place 2 at a time anyways. If they're just placing 1, they would still use a single clip applicator, which is still efficient.
Thank you very so much for answering the questions. And I wanted to ask you, when it comes to future improvements, what are some of the ideas that you have for the locking mechanism, if any?
So great question again. We were actually playing along with the single clip applicators do have a traditional locking mechanism that they use. So we were actually thinking of trying to somehow incorporate that into our design. It'd be something that when you pull it back, there's kind of like kind of where you see the space here, there'd be something where they kind of latch onto each other. And it would like, this would be, sorry, can you?
Yeah, I got you.
Like it, once it opens.
So if you have be able to squeeze and then leave it there.
Yeah, you just.
Yeah.
That was the main thing, and then of course, or you just asked about the locking mechanism, so yeah, sorry.
Okay, so great project. My question is related more to user error. I imagine you guys consider this, right? Like obviously surgeon expertise is very important. I imagine you would have to provide training to the surgeons with this new tool. But did you perform like a user error analysis or consider that at all when you were designing? And maybe did you add any mitigations to minimize that risk? I do think the locking mechanism would help a lot too, but.
So I'll take that one. So as it relates to user error, when we were thinking about that, we more so kind of were thinking of it in a way as to how can we design it so that there's not really a way to use it incorrectly. So when we're doing our static simulation, one thing that we did think was, okay, like, you know, just squeezing it as hard as you can, right? Is it still gonna break? Stuff like that. We were also looking at, you know, if you were to drop it, would it just fall apart? And I think the only other thing that I noticed when you guys were trying it was making sure that they're using it horizontally to open the clips. But we decided to, as well, thinking about it, if they use it the wrong way, that there's not really any harm in that. It's more so just kind of fixing it. And so we really kind of tackled that within our design and making sure that no matter how it's, even if it's used incorrectly, it's not causing harm or anything like that. It's a simple fix. And again, when we were doing our replication testing, we also, again, are seeing that the more that you use it, the easier it becomes and you kind of get the hang of it.
And just one more thing to add on to that, in terms of mitigating user error, we tried to keep the length, you know, as close to the literature values, like of what classic single applicators are usually like made up of, and like the spacing for the fingers as well. We tried to keep that as similar as possible, so surgeons don't have too much to get used to when using this new device.
Okay, let's give it up for
Thank you so much.
Let's give the judges a few minutes to gather their notes, and in the meantime, I call team number 3 to the stage. Team number 3. Wearable post-operative device for mitigation of capsular contracture in breast augmentation and reconstruction patients. Faculty mentor, Dr. Assad Mirza. Alumni mentor, Mr. Alex Ugarte. And this project is sponsored by Engineering Resources Group. Team members, Maria Parra, she's the project manager, Anthony Arenas, Maria Gonzalez, and Ashley Simpson.
right, let's give it up one more time for team number 2.
I think they're waiting for you to give, no, go ahead to start.
Yes. Well, the judges.
Okay. Good morning. My name is Anthony Arenas. My teammates, we have Maria Parra, we have Camila Gonzalez, and we have Ashley Simpson. And for our senior design project, we developed the implant displacement device 2.0. The implant displacement device 2.0, and with the purpose of preventing capsular contracture, which is a disease that happens for patients who have breast implant surgery. Clinical need. So over 1.6 million patients globally have breast implant surgery, with 300,000 happening in the United States. This is the #1 complication in breast implant surgery, happening in over 40% of patients. Revision surgery often costs between $5,000 to $6,000, and this is not covered in insurance. Therefore, that financial burden is placed directly onto the patient. Now, the current modality is currently manual massage therapy, which has four failures. Inconsistent technique, there's no objective feedback, and then patient compliance and the financial burden. Now, for our project scope, our scope was to develop a wearable post-operative implant device that would do the implant displacement therapy and also collect the tissue stiffness feedback. And this would be done within the budget of $1,500, and it would be completed by April of 2026. Onto our market requirements, we translated them to our design inputs, beginning with our first design input of getting at least a minimum of, a range of 1.5 to 2 centimeters of displacement. Then we had our maximum shift of our device of 5 millimeters. Then our operating pressure range of 0 to 10 psi. Then our minimum of 3 sensing zones around the breast, and then our actuation per zone of at least 6 seconds with a full cycle time of 18 seconds. Now our device does 3 things. Therapeutic device meant to displace the implant, monitor stiffness within the fibrotic tissue around the implant, and then lastly wearable. We want this to stay still to give us a consistent displacement of the breast. Now, why did we choose the air bladder? We did a household quality analysis, beginning with our piston-based actuation, which only received a score of 77. Then we did for our guided arc node with a score of 43, and then lastly the air bladder actuation system, which got a score of 95, which was our MVP. Then we have 4 subsystems, beginning with the structural subsystem. Then we have the pneumatic subsystem, our control and sensing subsystem, and our data output application. Now I'll be passing it down to Ashley Simpson.
Thank you, Anthony. So for subsystem 1, we integrated fixed PLA ladder molds with spackling vest, and the vest is divided into 3 cup regions: the superior, medial, and inferior. The outside of the vest was coated with epoxy resin to increase its structural integrity, and the body of the vest was also The body of the vest was also integrated with corset bonded wires. The vest is made out of 80% polyamide and 20% elastin. Subassembly 2 focuses on the pneumatic bladders. The bladders were manufactured in-house with a 0.3 millimeter thick TPU film, and they were heat sealed. They were heat sealed and are placed 3 different places: the superior, medial, and inferior. For the structural validation, we did simulations in SolidWorks to ensure that the applied pressure for the bladders could withstand the amount of the stress, which is 10 psi, the max 10 psi. For our control and sensing subsystem, it's 2 circuits. The air pump starts with compresses the air, sends it to a custom-made manifold, and then to 3 solenoid valves. Each solenoid valve goes to an air bladder, and the pressure sensors measure the internal pressure in each bladder. The Arduino Nano ESP32 is used for the air pressure activation circuit, and the ESP32 room is used for the sensing circuit. For our strain data calculation, we use a Wheatstone bridge. We use a strain gauge in a Wheatstone bridge configuration and amplify that signal with an HX711 module. For the biocompatibility of this device, TPU bladders were used because they are non-toxic, latex-free, and are used widely in medical applications. For the vest, polyamide and elastin was used because they are FDA approved and have been used in compression garments. However, the fiberglass epoxy resin cups and the spackling paste are for the prototype only, and for the future we have identified a more biocompatible material for each. For the fiberglass epoxy resin, we would use PEEK, and for the spackling paste, we would use RTV silicone. The engineering standards applied to this involves the biocompatibility of the device, the bladder integrity, the measurement accuracy, and also the fabric strength. No prior art combines all 4 elements of the IDD. The IDD senses, it actuates, it provides pneumatic actuation, it's wearable, and this establishes a new device. All right, now I'll pass it on to Maria.
Okay. So for the data collection, we use an app. We code in an app. At the beginning, we start embedding for a Wi-Fi, like a website. But we realized when we came to EC that it didn't connect in this Wi-Fi. It was like blocked. So we find out. I tried with the MIT creating an app in the World Cup. So and then we tried with the Visual Studio, and we create an app that collect the data from the SP32 using the Bluetooth inside of it. So to read the data. So we get the real-time graphs for the pressure and the voltage. So we have the protocol, the BP1, implant displacement test, the BP2, positional stability, BP3, pressure sensor accuracy, BP4, regional stability indication, and the alternative massage cycle. So the BP1, we put a tape across, and we put an implant inside the bag with some fluid so it can displace. And we turn on the machine.
And we check, put a dot in the middle, and we check how much it displays from up, down, and we measure it with a standard. We grasp the standard and the centimeters based to the doctor. We went and meet a doctor, and he told us how much it displays how much to display in the massage. From the longitudinal stability, we place a laser point in this area here, and we turn the machine for 15 minutes and see how much the point moved from the middle. For the reference of the pump, we connect it to here, like to the pressure sensor, and we also connected to another pump system to see what is the measurement it gave us to both of them. And we detect like a difference is very small, so what we read is actually the PSI that we actually need, like we have. So for the fabric fabrication, okay. Well, it's supposed to be 5 graphs. We did a data analysis, and that tells like what is the difference, like. So for the alternative massage cycle, it's supposed to go in a cycle, the bladders, and each of them works every single time, and they continue the cycle. And I'm gonna pass to Marina.
To test this device, we need tissue, but real tissue is not an option at a prototype stage. So we fabricated our own. 3 phantoms that you see here, 3 Baker grades, made from dragon skin silicone. It's an elastomer, chose for its tunable short 8 harness. We have our grade 1 baseline, which is this one, Phantom B. Uses a DS10 interior, or grade 2 to 3. And Phantom C uses DS20, which is a stiffest construct for grade 3 to 4. This is something that does not exist in clinical literature. Right now it's assessed by palpation, and there's no public or published threshold until now. We got Dr. Flores, who's a certified plastic surgeon, and he treated each phantom exactly as he would treat a patient. One session per grade. He palpated, and that's how we got these 2 boxes done.
30 seconds. Finish.
Okay, so this is a full distribution of measurements across the massage session per grade. Both metrics increase with contracture severity, and grade 3 through 4 shows the tightest constraints. Pearson R1 compares pressure and strain are perfectly linear across all grades. And Kruskel-Wallis P is less than 0.001 which compares the 3 grades and shows that they're statistically distinct. Our cost was approximately 962, which is less than 20% than a revision surgery. We also have to note that this has no predicate device. So the IDD 2.0 establishes a new category, and it's a predicate for future devices that they have to reference from. It's a de novo classification. We built a sensing system. We also made a new palpation grade to create new data and to publish new standards for palpation, and so that we can correlate palpation force to the new Baker grades with this device.
Okay. Thank you.
Thank you, guys. So you mentioned that your device provides displacement therapy and then also feedback on the stiffness, right, of the implant. So is the stiffness feedback meant to then like provide information on how much pressure the device should be applying? Is that like version 3.0 of the device, or did you guys consider that at all?
How much pressure we provide is we base it on the doctor, so gives pressure in each phantom, and that's supposed to be the pressure we're supposed to provide from the device. The stiffness is right now is not a way to tell how contracture is your implant, besides palpation or visual. So what we want to do is like apply the pressure that we provide in there, distinguish what is grade 1, right, grade 2, when you're wearing the device, so you have a scale that what you are, instead the doctor just looking at you and saying you are like this, you have this.
Thank you, team. When you guys were designing and the materials you guys chose, did you guys consider any environmental factors like rain, water, sweat, heat coming from the patient, and what kind of studies did you guys do?
For the hardness of the material, we try to look for a material that didn't bend or anything. For the sweatness, we grab, this is a post-chirurgical, like the material of post-chirurgical faja. We manufacture it in Colombia and we brought it here. And that material is made to be after surgery, so you sweat and everything with the surgery. But we don't take account right now, it's part cleaning days, but in the future it will be taken account.
My question kind of tags along Paula here. What quality controls did you guys put into the material when applying pressure? And also, what was the code you guys used to code the application and data collection?
Okay, we use Visual Studio and we use C Charge for the code. The data in the Arduino, in the microcontroller is P32, and we code it with Arduino. So we put all the coding in the Arduino, the data was sent through Bluetooth, and we receive it in the app, in the Visual Studio. It's a WP Windows app, and we receive it and transform it into data again.
So what was your budget and how much did it cost to make this device?
So our budget was an in-kind budget. We had 1,500 available, and we used 962. Between the electrical system, the support system, all the components, the tubing, pneumatic system, everything, we made a BOM to specify all the components, and yeah, that's what we actually use more because we did so many trials and errors, because there's no device that we can that we can reference from, but the device unitarily costs $962.
All right, let's get up for team number 2. And we'll give the judges a few minutes to gather their notes. And in the meantime, I call team number 4 to the stage. Team number 4. SAM, shock absorbing module. And what this is, it's a novel device for restoring natural gait dynamics in transtibial amputees. The faculty mentor is Dr. Manuel Mora. The alumni mentor is Mr. Deuce Erasmi. And the project is kindly sponsored by Bioengineering Labs Corporation. Project manager, Sheila Rangel. Other members, Sebastian Casales, Stephanie Amaro, and Michelle Gateau. give it up for team number 4.
Hi everyone, good morning. I'd like to begin by asking you all a question. How many of you know someone who uses a lower limb prosthetic? Well, for the few of you that do, it can be safe to assume that they've experienced some challenges. And for those of you that don't, hopefully today, my team and I can illuminate on one of their challenges and our proposed solution dedicated to improving their experience with a prosthetic. My name is Sheena Durkhead, and I'm joined by Stephanie Amaro, Michelle Gatua, and Sebastian Casares, working with Vivian Rojas in the Bioengineering Lab Court, and we are proud to present to you our shock absorbing module, which we will refer to as SAM, a device dedicated to restore the natural gait dynamics for transtibial amputees. Now I'll pass it to Stephanie to start us off with some background.
What if every step you take causes discomfort instead of support? Right? Now imagine that repeatedly loading over and over, but without the natural support of a biological limb. To continue, over time, this not only affects physical function, it also impacts confidence, leading to broader emotional or functional challenges in daily life, causing anxiety, depression, or common issues like pain and lack of gait control. Moving on, impact forces travel directly through the body, causing asymmetrical loading, excessive shear, and medical forces a residual limb, and also antalgic gait. This awareness logo reflects the wide range of individual impacted by lower limb amputation across different ages, lifestyles, and activity levels. This table shows that users prototype fit, stability, and mobility, highlighting the importance of effective force management within prosthetic systems. Before arriving to our final design, we went through multiple iterations, refining the geometry internal structure from an open lattice taper form with one spring to a more compact and cube design with 4 springs, with optimized features for string integration and load distribution. So now, honored guests, you can see here our solution. SAM is a 3D printed shock absorbing module that is integrated between the socket and the pylon of a prosthesis. Its goal is increasing the comfort and mobility of transtibia users, providing axial loading and control rotation. We designed this module to help users have a better lifestyle, enjoying outdoor activities with their family or friends, or maybe a simple thing that I do every day, walk my dogs. For the clinical impact, looking beyond our community, the need for a better prosthetic solution extends worldwide, with millions of people living with limb loss and many new cases occurring every single year. Our design addresses this need by improving load management through controlled compression, helping absorb impact and distribute loads more evenly. By reducing concentrated stress, it may help decrease discomfort and lower the risk of long-term joint issues. Looking at the business impact, our solutions present a strong market potential because it can be integrated into existing prosthetic systems. The below-knee prosthetic market is expected to grow from $2.5 to $3.5 billion by 2021, with an annual growth rate of 4 to 7%. Lastly, in the current modalities, we have the DuraShock Pilot, which has vertical compliance, but they're mostly limited into axial loading. On the other hand, we have the TT Pro adapter, which offers both shock absorption and control rotation, but they tend to add height and bulk to the system. Overall, these solutions involve trade-off in size, adaptability, and integration, which highlight the need for a more compact and efficient device. And now Sheila will explain the design table.
To fill in the gaps in the market research and current modalities, we will be targeting the average user weight for transtibial amputees, which is 85 kilograms, meaning that our device must withstand up to 1,250 newtons of axial load.
In terms of practicality, our device is lightweight and compact. So the total height must not exceed 50 millimeters and the total weight must not be greater than 300 grams. In terms of functionality, since there is an internal rotation of the foot relative to the hip, as well as shear stresses that can occur at the residual limb and socket interface, our device must allow for at least 15 degrees of rotation relative to its neutral position. In terms of functionality, our device must also have 10 millimeters of compression due to that initial step during the gait cycle that travels that shock upward, and 80% or more of restoration. To follow these design inputs, we have the auxiliary structure. Our auxiliary structure has been studied by many published papers, like Yang et al. In 2015, stating that it has a high energy dissipation ability as well as a high strength to low weight characteristic, which is crucial for our design as we want a lightweight and compact structure. We are utilizing the reentrant bow tie structure, and we do this by using the Timoshenko B model. The Timoshenko B model is important for analyzing how our auxiliary structure, which you can see in the bags, how our auxiliary structure is under bending and shear deformation and how it behaves in the compression. Here, following these equations derived from the B model, we found the axial stiffness to be 290 newtons per millimeter and the lateral stiffness to be 61 newtons per millimeter, having that complying for the rotation but supporting the axial load. And now for our simulations.
Thank you. So we conducted a pre-design study where we took a look at 4 springs versus 1 spring after looking at several configurations. Ultimately, as per the ISO 10328, we must meet 1,000,000 cycles, and fortunately the 4 springs was able to pass that, but unfortunately the 1 spring was not able to pass that. So we decided upon the 4 springs. Next, on to the stress analysis. So we created a homogenized continuum model to allow for to simulate the auxiliary core under compression. This is because of the large computational cost otherwise. So we applied a 1,290 newtons and achieved a peak bond resistance stress of 4.72 megapascals, which is less than 5.56 megapascals, which is the calculated homogeneous yield. Now, this is important because it means our module under compression will be able to restore to its initial position. Now, to the strain analysis, we had a 15.3% axial compression and a 9% lateral expansion. This is important for exetics because the auxiliary core conforms outwards, which allows us to reduce the localized stress as well as redistribute the pressure on the residual limb. Now for fatigue, as I had mentioned before, the ISO 10328 standard states that we must pass 1,000,000 cycles, and fortunately, ladies and gentlemen, our module was able to pass 1,000,000 cycles. Now, onto the factor of safety, we calculated that using the average weight of a transcendent amputee and a dynamic load factor, and we got a 1.18 value, which is greater than 1, which means that our auxiliary core under worst case scenario loading will be able to operate elastically, restoring to its initial position. Now I'll pass it back to Sheila to verify our design.
First, we were testing the dimensional parameters of our module. So with repeated trials using a digital caliper and digital scale, we found that the mean for the total height is 27.79 millimeters, as well as the total weight to be 104.9 grams. Moving on, we also performed a rotational compliance test. We had the module fixed at both ends and had a pulling force applied to the top to see if this 15 degrees of rotation was allowed and more. In this plot, we can see that as the degree of rotation increased, so did the torque, and we can see with the line of best fit, there is a strong relationship for controlled torsional stiffness, indicating we do have that module restoring back to its neutral position. Moving on, we had a static ultimate compression test. We were following the ISO 10328 standards, where we had our module under 2,240 newtons of force, then to 4,480 newtons of force, each for 30 seconds hold, and in this clip we can see our module restoring back. However, we also wanted to measure the restoration for our targeted 10 millimeters of compression. So in this slide we can see we had 3 specimens, and each with 3 trials, where we measured the total restoration to be greater than 80%. And finally, we performed an aggressive durability test. This was utilizing a hammer drill which had a setting of 4,400 beats per minute, which if we translate to hertz would be 73 hertz. And if you compare this to real life walking frequency, which is about 1 or 2, or running frequency, which is about 3, 73 hertz is much, much higher. However, this test was a proof of concept that our device has the potential to receive that dynamic energy input, and our future work will consist of dynamic cyclic loading under standardized loads. And now for regulatory assessment.
Thank you. So our device classifies as an FDA Class 1 prosthetic accessory since it supports the prosthesis without introducing high-risk interaction. Because of this, it falls under general controls, making the approval pathway much more straightforward. We focused on key ISO standards related to structural testing, its heat, material properties, and energy displacement, or energy dissipation to ensure for reliable performance under real-world loading. In terms of cost, it's very cost-effective since we succeeded in going below the budget by using additive manufacturing and simple components to ensure for reliable production, efficient production, and ensure that it's scalable to existing shock absorption systems. Additionally, SAM is adaptable for patients of varying weight and activity levels across a wide range of healthcare settings. We also reviewed existing patents. Where most designs focus on either elastomers or mechanical linkages, our design differs by combining an outside structure with a spring system that allows for a more customizable and potentially improved shock absorption. Overall, we succeeded on many fronts, but I'll focus on our main, that we successfully verified and tested the functional module, validated its mechanical behavior, and evaluated its manufacturability, cost, and regulatory considerations. For future work, we plan on adding an outer casing that will increase its durability and protect against environmental exposure. Dual material printing is considered in order to ensure that it's flexible and increased in strength, as well as for better control deformation. We can optimize the spring system to allow for better match for different users, and integrate sensors to provide real-time performance feedback. Additionally, we plan on, as we plan on developing our device more, we can collect more data for more statistical analysis to validate performances across a wider patient population. Lastly, we'd like to acknowledge our Professor Hamid Cherasani, Dr. Michael Christie, and we'd like to sincerely thank our sponsor and mentor, Dr. Emmanuel Mora, for his mentorship, and Julian Rojas for his sponsorship, as well as the many professional contacts who provided us with their time and expertise. Thank you.
How did you guys determine placement as far as directly under the, why not at the angle?
So our device has the attachment here for screws as well as here at the bottom where it can be interchangeable. So for the purposes of our example here, there was this feature of the foot that the prosthetist gave us, but it does have adaptability to be between the socket and pylon or between the pylon and the foot.
Okay, so then how would the user determine what's the best fit for them?
So users typically get mentorship from their prosthetist, and the prosthetist decides what is better for the residual limb, and so they can focus on whether it can be at the top or at the bottom. So our focus was making sure that it can be adaptable so that the prosthetist can have more options for the user.
I think you mentioned that the service life was minimum 1 million cycles. How does that translate to how long you expect the component to last for the average user? And then, how often would they have to replace it? And then I don't think you mentioned how much you would expect it to cost, assuming insurance wouldn't cover it.
Thank you, that's a great question. So, in terms of cost, it is a very cheap product to manufacture, considering that it's mostly focused on 3D printing. The springs, we doing testing and for standardized springs, it's supposed to last 1 million cycles. We can do further cyclic testing to have a better grasp of the lifespan of the material, since we couldn't we didn't have the proper material or equipment to do that testing. However, yes,
I think she's asking why 1 million cycles.
Yeah, I can add on to that point of 1 million cycles. So the 10328 specifically mentions 1 million cycles because that corresponds to, on average, the number of steps people take a day is about 5,000. So when you divide that and do the calculations, it's about 200 days, approximately 200 to 300 days, and that allows the user to, walk around for a good amount of time. And any other questions? Oh, sorry.
Great job, guys, by the way. Thank you. And so I wanted to ask you, mentioned there will be some encapsulation ideas for the environmental protection. What are some of your future ideas when it comes to protecting the material from the environment?
Thank you. Currently, we are thinking on different 3D prints. So, PETG is a possibility that we can have as an environmental protector. Another thing is encasing it with epoxy or another solution that will protect it from weather and different materials. Maybe not necessarily, maybe a metal. It's still, we're not 100% decided on, but it's still up in the air when it is open.
So apart from the verification that you did of the technical testing, were you able to test for during gate, there are different phases, right? The initial contact, mid stance, heat strike, toe off. So were you able to test any of that?
So to be able to test during the different steps of a gate cycle, we would need to utilize an equipment that can simulate that. And so our best approach was having the simulation for static compression, but for our future work, we do plan on including some dynamic testing to see how it would perform during the full gate cycle.
I have a question and a comment. For the question, what did you guys do or incorporate into your device to make sure that the patient is stable? And for the comment, maybe next time let's stray away from politics. And because we're engineers, we're biomedical engineers, we care about the human patient's health, and we don't really go into politics like that. And also, especially after we're actively breaking the international law in multiple areas of the world.
So could you repeat your question?
Stability.
So for stability, we included 4 springs, which in comparison to 2 springs would mean that we would have to choose whether it be to the left or the right, or the top or the bottom. So we wanted to include 4 springs to have that equal distributed load. As well as for stability, we wanted to ensure that there was proper contact between the 2 components, which is why we utilized nuts, flange nuts, as well as washers to secure those screws in place.
And additionally, we initially had a tapered shape, and we decided on the cube because the even distribution allows us for a more stable shape and more even distribution. Any other questions?
Okay, let's give it up
Thank
for
And we'll give the judges a few minutes to gather their notes. As team number 5 takes the stage, team number 5 taking the stage. Automated processing system for optimized microbiota extraction. The project manager is Jennifer Bokin, I hope I pronounced it correctly. Faculty mentor, Dr. Jessica Romelo Roman, and the alumni mentor is Ms. Renate Brand. And the project is kindly sponsored by RDIC. Let's give it up for team number 5. Team number 5.
Good morning, my name is Jennifer Bokin Sidu, and we are team number 5. Team number 5 consists of myself, the team leader, Natalie Hidalgo Gato, Marco Garcia, and Camila Hakami. Our sponsor is Argent Technologies, and today we're really excited to present our senior project, an automated processing system for optimized microbiota extraction. Now, if you look around you, 1 in 6 people will experience Clostridium difficile, also known as C. diff, which impacts your gut microbiome, and this is primarily driven by high antibiotic use, but also in elderly patients who have an immunocompromised system, as well as transmission in healthcare settings. Now, having a healthy gut microbiome cannot be understated. It allows our body to perform daily essential functions such as immunity health, digestion, and overall health. However, disruptions to the microbiome does lead to various complications such as severe diarrhea and colitis, which is the inflammation of the colon, the largest part of your gastrointestinal tract. Of course, this leads to a reduced quality of life, and about 50 patients who experience C. diff will experience RCDI, also known as recurrent C. diff. However, this is currently mitigated through fecal microbiota transplantation, also known as FMT, which is harvested from screened healthy donor samples, and this aids in the restoration of the gut microbiome. This is an emerging treatment, meaning that there is proven success rate in patients who suffer from C. diff. Now I'll pass it on over to Camila to talk about the growing need.
Thank you, Jennifer. As Jennifer previously mentioned, 1 in 6 people develop C. diff with a high recurrence rate of as much as 50%. By 2030, the FMT global market is expected to exceed $1.6 billion with an annual growth rate of 5 to 6%. Our earnings target will be $1.875 million with our device selling for $25,000 across 75 North American sites. As you can see right here in our graph, this is how much the FMT market is valued currently. So our system will only focus on the first step right over here. It essentially starts with getting stool from the donor, then mixing it with a common blender, and then filtering out with a cheesecloth, getting the final product. That's the manual preparation. However, there is another type of modality, which is the semi-automated fecal microbiota processing system. However, both share the common disadvantage that they have very ineffective filtration, which our system will address this. Now I'll pass it back to Jennifer for clinical needs.
Thank you, Camila. So as Camila highlighted, current modalities do have their challenges. This includes an 100% filtration clogging rate, very heavy manual labor due to the complex and time-intensive intervention from the clogging as well as the setup of the system. This does limit sample productions to only 3 production runs per day. And of course, this does result in lack of consistency and lack of reproducibility. Our proposed solution is simple. We reduce inefficiency, increase operator safety, and improve reproducibility as well. And with our system, we were able to achieve and address these challenges with a project budget of $1,500. And I'll pass it off to Natalie for market requirements and design inputs.
Thank you, Jennifer. For our market requirements, through conversations with our sponsor and research in the medical literature, we identified the most crucial factors for our device and translated them into design inputs. On this next slide, you'll see some of our most important ones, starting off with a high-speed RPM on our homogenizer to ensure full homogenization of our product, followed by a minimum CFU count of 1 million CFU to make sure that there was no bacteria damage through processing. And lastly, we want to make sure that this device supports enzymatic cleaning to ensure no cross-contamination in between runs. So with those design inputs, we came up with 3 design concepts. The ones I'm going to present today focus on the filtration module of our device. So the product has already been homogenized by the time it reaches here. Our first design concept takes us back to fall semester of senior design, where we started with a set of inline filters and a backflushing method to quickly and efficiently remove those caked-on layers that form on the filter. However, we quickly realized this was not a solution for our clogging, just a quick way to mitigate it. Our second design concept was a scraper arm. So this was intended to scrape off those caked-on layers that form on the filters, but due to the complex geometry and issues with the sealed holes, this became challenging. Our third design concept is a screw auger filtration method. So this uses a screw auger and a cylindrical mesh filter wrapped around it, and it works by compressing the product against the filter and efficiently separating our liquid viable product and our solid waste. This was chosen as our MVP. So to reiterate, this has our homogenization module with the emulsifier and initial chamber, and then a pump and a valve will move the product to the filtration module here with the screw auger, filter, and then our final compartment chamber will hold our viable liquid. For our simulations, we ran 2 main simulations, one for the homogenizer and then one for the screw auger. For the homogenizer, we used MATLAB to do a shear stress analysis of the bacteria while it's being homogenized, and we used a variety of viscosities and the co-equation, and our results showed that we did not meet the max stress of 100 pascals, therefore we had successful results. And then for our SolidWorks, we did a rotational stress analysis on the screw auger, and there was no significant plastic deformation, therefore leading us to successful results as well. I'm going to pass it off to Marco now to talk about manufacturing.
Thank you, Natalie. So as you can see here, we've divided the system into 2 main subsystems, The first of which is our homogenization system, which consists of a commercially bought homogenizer, a main chamber where the homogenization takes place, and a pump to move everything to our second system, really the main focus of our project, that being the screw auger filtration system. And the way the system works, as mentioned previously, is with a rotating screw auger you can see right there that is encased by a filter that compresses the material and removes the solid waste while maintaining the usable liquid material, which is captured in that chamber right there. We had two main methods of manufacturing. The first one was purchasing pre-made parts from McMaster-Carr and then closing some gaps with some trips to Home Depot, and then 3D printing the two main chambers. As you can see here, that is one of the earlier versions of this chamber being printed. We ran a series of design verification tests in order to ensure that we met the inputs that we laid out previously in this presentation. Some of the most important ones include the RPM measurement test, in which we used a laser tachometer to ensure that the homogenizer that we purchased met the metrics that we set forth in order to break up larger particulate without damaging bacterial viability. And we ran a series of tests across the entire range of our RPM values, and we found a percent error of only 1%, meaning that this was a reliable device that we could use in our system. The next and most important test you can see right here, which is the CFU test to measure bacterial viability. If our method produces product with significantly lower bacterial viability than previous methods, then there's no point to creating this product at all. So this test was extremely important. In order to conduct it, we created a simulated stool sample made from yeast and water and then passed it through our system. We then compared its turbidity to a standard tube, you can see right there, which estimates to about 1.5 times 10 to the 8 CFU. As you can see, the turbidity is far greater in our collected sample in that bucket than in the standard tube, meaning that we are safely within our metrics. We then repeated this test 5 times and ensured that 100% of the time we pass that turbidity with flying colors. This method is viable. Our next and final test was after each one of those 5 runs, we used protein test strips, which we applied to the filter within that chamber right there, judges. And you can see here that it, of course, came back positive because there was bacteria on the filter. This is expected. The problem is if we were to then run another sample through the system, there would be cross-contamination, and that could be very dangerous for the bacteria. So we used enzymatic cleaner, flushed it through the system, and then water to remove any leftover material, and it came back negative. We ran several more tests in order to ensure we could reproduce this, and struggled slightly. We believe this is mostly due to false positives created by the enzymatic cleaner, which might show up on the protein test strips. We still believe enzymatic cleaner is ideal for this due to its ability to remove biofilm, which products like bleach can't do as efficiently. Our total budget was at $1,500, with $1,000 going to manufacturing and $500 going to verification testing. I'll now pass it on to Camila for some intellectual properties.
Thank you, Marco. So based on our pan search, we found that there were no conflicting technologies. There were, however, 2 main pan opportunities based on our 2 subsystems, but essentially it highlighted just how novel our system truly is, as well as how much potential for panability we truly have. So our system effectively homogenizes the stool sample. It is significantly less prone to clogging compared to the previous design, and it is also very quick to assemble and disassemble, averaging for less than 5 minutes. So as you can see right here, we have the chart again, and essentially we covered all our bases that the kernel modalities had many disadvantages. This highlights just how much the FMT treatment is needed for the market. And now I'll pass it on back to Jennifer for regulatory assessment.
Thank you, Camila. For our system, due to moderate risk of operators handling biological material, our system would be classified as a class 2. This, however, would be mitigated to a closed, controlled fluid pathway and validated cleaning procedures, as well as risk assessments and further verification tests captured in the QMS, quality management system. For our system to enter a 5-tank, it would follow a 5-tank clearance pathway, meaning that we must demonstrate significant equivalence to an legally predicate device, and then as well as showing similar technological characteristics. And below you'll see applicable standards all the way from ISO, FDA, IC, and ASTM. Looking ahead, improvements improvements to our system include material upgrades. So transitioning from 3D printed materials to 306 or 316 stainless steel for better reliability, as well as cleaning such as sterilization, autoclaving, as well as friendlier user interface by integrating an HMI module, enhanced contamination control by adding a ceiling housing, and as well as system expansion by integrating a sensor and feedback for closed loop automation. And with that, we want to thank our sponsor, Omar Lopez from Art and Technologies, as well as our professors and faculty, Dr. Christie, Professor Shahrastani, and Dr. Ramela Roman, our alumni mentor, Rina Ran, as well as Dr. Mirza and our peers for their help and contributions. These are all of our awards cited. And with that, we want to thank you for your time and are open for any questions.
I'm so glad that you guys said that you're looking at putting a splash guard on there, because I'm so concerned. But no, good work. I do have a question. As far as different waste, different fecal matter has different consistency, how did you select a filter?
Yeah, that's a good question. So that's a big part of this and something that is a little bit out of our control since, we don't have control of those samples. So it's unstandardized, but we did a lot of research on what exactly is in our product and is a lot of fibers, as we mentioned. So yeah, choosing a filter, we have a pore size that would allow for only the bacteria to fall through there. And as for clogging, that's also where our biggest challenge was. In this system, we can reverse the auger to kind of, if it gets clogged, we can pull it back a little bit so we can control that clogging. But yeah, our pore size filter, if we go back to one of our DIs, we can review that as well, but to account for that.
Just a quick follow-up is that we did test the pore size using a verification test. That was not brought up for the sake of time in this presentation. But we ensured that our pore size was usable for the expected clumping, and as Natalie mentioned, the variety of viscosities that come with working with stool sample.
What would you say was your biggest challenge while doing this project?
So one of our biggest challenges was actual manufacturing of everything. So originally we planned to have everything stainless steel, so it's medical grade, but of course, some constraints came up and we ended up 3D printing some of our chambers. So once we got all that, kind of putting everything in a way that made sense and that could be used in a clinic. So right now, maybe it's not the most ideal because it's kind of off the table, but positioning everything in a way that made sense for assembly, disassembly, and cleaning was a bit of a challenge for us.
One of the examples, we had to make a lot of on-the-spot corrections in order to get this just right. For example, the material we used absorbed a lot of water and then would slowly leak it out over the next several days. Imagine that with stool sample, not ideal. So we actually used a sealant spray, which we used on both of the chambers and the lid, and it worked extremely well, and we have not had that problem since.
I want to also highlight that this current modalities, they don't have a standardized process for even harvesting healthy donor samples, so there's a lot of room for variability right there. So that's another challenge added onto our senior design.
Okay. One more question.
So in terms of cost compared to the current modalities, can you guys please explain how would the clinics be saving money? I mean, you guys talked about time consuming, but and from a cost perspective and thinking about the space that it takes, right? Did you guys take that into consideration?
That's a great question. We did take that into consideration. So the main problem with current methods is not just how manual they are, but they take a lot of training on top of it in order to ensure a sterile environment. Anything working with materials such as stool does. This device would allow, another huge thing is it has to be outsourced a lot of the times. It cannot be done in-house. With this system, the training is cut down and thus you don't need to outsource. Instead, hospitals could buy this themselves and do it in-house, which will save them a lot of money over the long term after just one purchase rather than constantly having to pay for outsourcing.
I think,
one more question.
Yes.
Thank you so much, guys, for your presentation. I also wanted to ask you, let's say I'm a nervous patient and I see this machine. It looks a bit intimidating to me. So what are some of the ideas that that you have in mind, so that it's more patient-friendly in that sense? And could you also give me an idea of how it works?
Sure. So to address that, the way it works on the pamphlets we handed out, on the back page is a QR code you can scan to watch our demonstration videos, since unfortunately we couldn't have it running here. But yeah, so the patient would not actually see this machine. This is more intended for the clinics themselves. So as we mentioned in one of the clinical needs slides, this was the first part of the fecal microbiota transplantation. So after we get this product, it's going to become centrifuged and go through other processes. So that the patients won't exactly have to see this. There's a couple different methods to actually deliver the treatment. There's oral pills or other ways you can get it. So they would have a much more normal doctor experience and they wouldn't see this device. So yeah, they wouldn't have to worry about that scare. And I'll quickly walk you through before you watch the demonstration video.
Patients in the other room.
Yeah. So we start here with the, as you saw, the yeast in the water for our purposes, and then this homogenizer will turn on and mix. And then this is the valve here, we'll turn on the motor, open the valve, and turn on the pump valve, and then this motor. This motor will turn the screw auger, so the screw auger is hidden in here right now. And then the product will go through the filter there, and the auger will help filter it out. Everything is saved here. The solid waste will come out here, so we intend to have something here to catch that. And then the viable liquid can be released through there. But again, that's in our pamphlet as well if you'd like to watch the video. Any other questions?
Kind of looks like it. Quick connect, quick disconnect.
Yep, it's actually supposed to do that, believe it or not.
All right, thank you very much. That will be team number 5. Let's give it up one more time. Team number 6 is now on the stage. The project is sponsored by Neurofit 360. The faculty mentor, Dr. Raj Kulavirtha, and the alumni mentor, Mr. David Mongrue. Project manager is Aaron Tahiro. Other members, Mariol Duran, Lucas Menendez, and Antonio Herreros. Project is Healing Hand, rehabilitation device for restoring hand spasticity after neuromuscular injury. Let's give it up for team number 6.
Good morning, everybody. Thank you so much for coming. We are Team 6. My name is Aaron. This is Lucas, Antonio, and Mario. And our sponsor is eRomaine, and our faculty advisor is Dr. Kulavirtha. So our project is going to be Healing Hand, a rehabilitation device for restoring hand spasticity after neuromuscular injury. So Antonio will talk about what neuromuscular injury is.
Thank you, Aaron. So neuromuscular injury is when the communication between the brain and muscle is disrupted, leading to hand motor function, like to impaired hand motor function. So it also proceeds to hand spasticity, which is nothing else than stiff hand and involuntary muscle contraction. So 86 million people around the world experience hand spasticity, and even though advanced technology exists, they still remain expensive. And many other regions, they just rely on inconsistency or maybe even lack of therapy. So current modalities to enhance plasticity is in injections, medications, and physical therapy. In this project, we focus on physical therapy because it is the first approach to restore neuroplasticity. So this creates a cycle where the patient has to make frequent trips to the clinic to attend for physical therapy sessions. And this, they always have to incur in ongoing expenses, making the therapy a very inconsistent and difficult to continue on in the future. So according to the Institute of Medicine, effective patient care, it should empower the patient to take an active role in their recovery. That's why our solution, a soft pneumatic rehabilitation glove, will not only make an impact in the therapy field, but also in the healthcare system. And the therapy field, it provides repetitive, specific task movement to restore neuroplasticity and recover hand motor function again. And the macro impact, which I like to call, is the healthcare system will take care of the previously mentioned cycle. Yeah, more or less to summarize what I'm trying to say is that this device will improve the consistency and accessibility of the therapy. So to go over the macro requirements, the first one I want to talk about is that the glove must enable functional hand motions during the actual rehabilitation. And the second one is that the device must support therapeutic hand rehabilitation during the session. So for the design input of the first macro requirement is that the glove must cause joint angles motion between extension and flexion equally of 60 degrees or above. And in the second design inputs, we have that the system shall measure relative muscle activation with an accuracy of 90% or above. Now Lucas will go over our design concepts.
Thank you so much, Antonio. So as I was saying, we need a glove that can help you expand and contract and expand your hand. So our first design concept that we came up with was this basically a balloon or a whoopee cushion, which just when it deflates and then it causes your hand to contract, and then when it inflates, it causes your hand to expand. And like this, it would be very simple production. However, it's very problematic in causing single individual finger motion, so you can't just individualize one finger. And it also does not provide a full range of motion. The second idea that we came up with was a spring-loaded glove. However, this could provide individual finger motion that we previously mentioned, but it's expensive and it's very difficult to provide flexion with a design like this. So this led us to the MVP. This led us to our MVP, which is a soft pneumatic glove that enables both extension and flexion to support therapeutic hand rehabilitation. And it's going to be utilizing an EMG system. So it's basically going to be reading EMG from your hand, and like that, whenever you contract your hand, that the device will act on that, and then it would extend, it would contract. And then if you were going to extend your hand, the device would read that, and then it would extend as well. So up on your table, you see two different pieces of fabric, right? You have one that's stretchy, which is that black one, the one labeled number 2, and then the one that's very taut, very rigid, which is number 1. Right? And these two different fabrics are what's going to make the actuator, which causes that bending on the hand. So you can imagine if we were to get two of these low stretch fabrics, two of these, the green ones together, and stitch them together, you end up with like a little chamber like this. And then if you were to get a high stretch fabric and then put it on top of that, sew it together, you end up with 2 chambers. This is your number 3, right? And that's what we're putting on the back of every glove. So you see that there's a high stretch chamber and then there's a low stretch chamber. And if you want, Aaron will talk about that later. So you can imagine if we were to run tubes through these and inflate that high stretch fabric, that high stretch is going to want to deform, it's going to want to displace, right? But that low stretch fabric on the bottom is going to resist that deformation because it's so taut, it's very, very tight. So this causes a bending motion and differential strain, right? And you can imagine if we go ahead and we inflate that low stretch fabric, the opposite is going to happen. It's going to become rigid, it's going to become taut, and it's going to straighten out. So we want to confirm these ideas on SolidWorks. So we did that, and then here you can see when you inflate the high stretch fabric, there's high displacement along the top and very little displacement along the bottom. This kind of infers that it's going to be a bending situation. And then we also have a high factor of safety throughout this actuator. Then when we inflate that bottom one, that low stretch fabric, you see that there's uniform displacement throughout. So there's the same displacement on the top, the bottom, and the sides, right? And this basically just means that it's elongating instead of bending or changing shape. And additionally, it also has a high factor of safety throughout. Now passing it to Aaron.
Thank you so much, Lucas. So going over the theory, essentially the same thing. When you have that high stretch, you inflate it. You'll have the bending motion, and the low stretch, you have the elongating, extending motion, which is validated by the motions, the SolidWorks simulation. So let's go over the manufacturing cost. So the material is 620, which is relatively low with an overhead of 90. So the total manufacturing cost will be 710, below our $800. So our actuator manufacturing, as Lucas had mentioned previously, the visual, and as you can see on your tables, which you probably already inspected, the top is going to be the high stretch, which is the black, and then the low stretch, which is the green on the bottom, and then inside the pocket as well. So does it work? When you inflate, we have an actuator right here, we inflate it, and then as you can see, it bends. So knowing that, we then mount it onto the glove with our control box to then begin verification test. So I want to begin first by talking about the anatomy of the hand before we talk about verification. So we're going to look at the 4 primary digits on the wood hand and fixture. So it's going to be the MCP joint, the PIP, and the DIP joint. So then from this, we're going to start our verification. So our verification test has an acceptance criteria of a minimum of 60 degrees for all the joints. And we're going to try the flexion out. So this is a video of how it would look like. So as you can see, it does cause flexion. So we then use a goniometer to then check the degrees of change for each one. And from that, we got these results. So as you can see, it's statistically significant. It's above 60 degrees for flexion, passing that test. So we then began extension, same criteria, a minimum of 60 degrees for acceptance. And we did a naturally curled and then using the extension. So this is a video of how it looks like. And as you can see, it extends up. So we did that several times, and we got this graph here to show that it's statistically significant, well above 60 degrees for all the joints. And as we can see for the verification, it passed both tests. So we now know that the mechanical aspect is sound, but we need to incorporate with the EMG to see it cause the rehabilitation.
Thank you, Aaron, for passing me. After seeing the glove performance using both flexion and extension, we then consider a next step, which is like creating a system responsive to the user. So that's where the EMG comes in. So how it works is like the EMG reads the flexor and extensor muscle and send it to a microcontroller, and where it analyzes it and send it to an air pump that made the actuators to flex or extend the fingers according to the user intent. To verify this, we did 50 trial samples where we included flexion, relaxation, and rest. And according to our results, we got 100% of accuracy out of the 90% of our success criteria. Here we are just showing our verification for our 11 design inputs. According to this table, they're all passed. Now, along the performance, we follow the engineer standards, and the 3 main ones were the biocompatibility on the skin contact. The other one will be like the electrical safety features, where we incorporated emergency shut-off buttons, and also we maintain a well-documentation traceability following the ISO guidance. Now moving to our next slide, we have the intellectual properties, where the 2 main innovations are the actuator's mechanism that will help with the finger movements, and the second one will be the EMG feedback that will allow the user to remove their own rehabilitation. Now going into our summary of accomplishment. Overall, our design has characteristics of having a low-cost, lightweight glove with EMG system incorporated that has a smooth and bi-directional hand motion by using a soft fabric actuation mechanism. For our future work, we consider having a mobile app that will track more personalized user therapy progress. And this is the end of our presentation. Thank you so much for all the people who collaborated in this project. Dr. Christie, Dr. Sebastiani, Dr. Roberta, our sponsor Romain, and our alumni mentor, David Margaret. Thank you.
Thank you guys, that was great. So it sounds like a big part of your value proposition is that you're not just providing movement assistance, but you're recording EMG signals and then adjusting it based on that. So I'm just curious, like what evidence is there to suggest that that's better than just like a pre-programmed movement assistance system?
Yeah, so thank you for the question. So yeah, in terms of if there's improvement, yeah, there's literature review that shows that when it's active intent, rather than like just a cycle, repeated cycle, when it's active intent on you trying to make that motion, it's gonna create neuroplasticity, which helps over time to let you get that motion and kind of refine it. The same way like riding a bike or anything, you kind of refine that motor skill.
Are there different grades or levels in specificity and variability in patients? Have you considered that?
Yeah, so in terms of variability, that is a factor, calibration, because as you can know, like there's gonna be a difference between, let's say, a younger person getting it than an older person. There's gonna be different muscle mass, and that also leads to different like electric potential. So that's definitely a factor, calibration for each user to make it like more personalized. So yes.
So you considered it as a part of your design?
Yeah, yes. Yeah, for the EMG, yes, we considered it. Any other questions?
Yeah, just more for information and awareness. So how long is a patient expected to wear that? And so then that's one question, and it kind of follows up because I see the cables running through it. Are they expected to be close by that machine, for that period of time?
Yeah, so this is a rehabilitation device, so it's not like you're just gonna be walking around carrying it around. So our project sponsor, Dr. Guy Romain, and he's gonna be basically saying, okay, you're gonna go home and for 1 week straight, do 50 cycles a day and et cetera, et cetera. So it's gonna be that physician that's basically going to be telling you, like it's like an at-home workout or just a at-home therapy session. So it's not like a day-to-day use. And then,
Yeah, and just to add to that, that's the main issue he had given us was that when you have the rehabilitation, it's that after some time, the patients tend to get like, not late, a little bit lazy. They'll stop like doing the motions and stuff. So he's like, okay, that's why we wanted the future work is the app. You want to have just more like, for example, you get a notification reminder, oh, like therapy. Have something to keep you attentive to doing the cycles every day.
Thank you guys for answering all the questions so far. And I want to ask you, how do you plan to make the box a bit smaller? How do you plan to make the box smaller?
Oh.
So the patient can take that home?
Yeah, so definitely there's a prototype. We would definitely miniaturize it. There's definitely ways to optimize it. Like I wanted, like for example, it was more time limiting, a PCB, like a PCB board, that type of stuff. But 100% this could definitely be miniaturized. The only problem is the solenoid valves do take up space. So that's the only thing that makes it not easy, like for example, put on your arm or something. But yeah, 100% we can definitely minimize it. Make it look less intimidating.
I just have a question regarding the safety behind it. What controls did you guys do behind, I guess, controlling how much it extends and contracts? Effectively.
I already have it in my hand. So we have a pressure limit of 70 kilopascals. So basically, once it gets that pressure, it's not going to keep continuously inflate, so it just doesn't like keep expanding and just blow up, right? Also, the fabrics have a very high factor of safety, so if you can literally feel them like that, that's like it's hard to break. You can really tug on it, it's not going to break. And we also, in addition to that, we also have an emergency stop button. So for whatever reason, it's the big red button. So if for whatever reason you feel uncomfortable, it's not really working, or you feel like it's going to break, you can just hit that button and it stops.
it up for team once again, let's give the judges a few minutes to gather their notes. And in the meantime, I call team number 7 to the stage. Team number 7. The phantom model for assessing the performance of cannulation devices in stenotic femoral arteries. The project is kindly sponsored by Circulatech, faculty mentor Dr. Josh Hutchison, and alumni mentor Mr. Sebastian Geraldo. Project manager is Christopher Tarafa. Other members, Oscar Rosendo, Alejandra, Aracita, sorry, and Rachel Puerto, sorry. Apologies. But yes, phantom model for assessing performance of cannulation devices, stenotic femoral arteries. Let's give it up for team number 7.
Hello, we're Senior Design Team 7, and this is our project, a phantom model for assessing the performance of cannulation devices in stenotic femoral arteries. My name is Christopher Tarafa. I'm joined today by Alejandra Arascaeta, Oscar Rosendo, and Rachel Puerto. Our sponsor is Jake Pisker from Circulatech. This here is Paul. Paul is a 76-year-old man who is for his entire life been suffering from episodes of chest pain. Today, however, his pain was so bad that he decided to check into the ER, where they found out he's actually suffering from ventricular tachycardia, something that greatly increases heart rate and leads to heart failure. Paul is one of over 900,000 people annually in the United States suffering from heart or lung failure, and that amount of cases is just growing by the day, with it now accounting for over 36% of cardiovascular disease deaths, which is the leading cause of death in the United States. The doctors decided the best way to help Paul would be to start him on femoral arterial extracorporeal membrane oxygenation, which is a way to reoxygenate the blood outside of the body. How they do this is there is a cannula inserted into the femoral vein that draws blood out of the body. It is then pumped through a blood oxygenator and back into the body through a perfusion cannula in the femoral artery. Now, while this is something that can save the life of Paul and many others, it comes with the risk of something called distal limb ischemia, which is a restriction of blood flow to the lower leg. This happens because when a cannula is inserted, it pinches down the artery beyond the cannula, and pre-existing stenosis, as well as the insertion of the foreign body, causes the artery to squeeze down around the cannula as it's been inserted. This can lead to an up to 90% reduction of flow down the leg, which leads to patients having a 15 to 25% risk of developing distal limb ischemia. Now, as I mentioned, and you can see here, there's that pinching of the artery, up to 90% of it, which causes no flow down the leg. This comes with these complications, the first of which is the cost. When this complication happens, it can cost $20,000 to $100,000 depending on the severity of it. Also, it comes with a 1 to 5% chance that patients will have to have their limbs amputated. And some studies even report up to 60% mortality rate when this occurs. Next, I'll hand it off to Alejandra to talk about the current treatments.
Thank you, Christopher. The current modalities that exist right now, the main one is the distal perfusion catheter, in which a catheter is inserted into the stenotic artery to provide blood flow down the leg. Physicians don't often do this because it puts the patient through an extra procedure, and this obviously brings risk. Our only competitor on the market right now is the Bonova biflow cannula, which ultimately fell on the market because the blood was getting stuck on this elbow that you can see right here. The clinical need of our project is to provide distal and proximal blood flow to ECMO patients without the need of a distal perfusion catheter. What this does is lower the ischemic risk. Our sponsor had an idea of a bidirectional flow cannula, and our contribution to this will be a research and development tool that enables cannula development. I would like to present you all with the ACOR ECMO model. We create a bench-to-backbone model that is able to replicate flow with a pump. We have a custom-made femoral artery, and overall, we're able to maintain control of the system. Now I'll pass it up. Why build our model? Nothing right now on the market fit our needs, therefore we build our own. Now I'll pass it down to Christopher to discuss the development process.
When we were considering development of this device, we decided there were 3 main requirements that we have to meet. First was being able to recreate the ECMO flow model itself. Next was being able to replicate femoral stenosis that leads to distal limb ischemia. And third is having a control system that is able to set the performance of the cannula and monitor that performance so that we can make sure it is doing what it needs to be doing. Below that, we have a design table with our most critical market requirements and design inputs, which we will get into more as the presentation progresses. So focusing on the ECMO flow loop, we defined our requirement as being able to test multiple different cannulation devices and strategies with our single ECMO flow loop. We decided to do that by creating a standardized connection interface and modular incorporation of all of the parts of the device. Now here we have another picture of our flow loop where we have the flow path outlined in red. And there, circled in green and enlarged here for you guys to see, is our custom cannula interface module, which I'll hand around for you guys here. This allows for us to be able to insert the cannula and secure it when we're doing testing. This is followed by a demonstration video where you can see us inserting the cannula into the system as it will be done, placing it within the femoral artery, and then we can trace the flow path. We draw liquid from a reservoir to our pump, it's perfused into the femoral artery module, and we follow it around the tubing system that we have laid out, where pressure sensors and flow sensors collect the data that we need. Now I'll hand it off to Oscar to talk about our second requirement.
Okay, thank you, Christopher. For our second requirement, we aim to replicate distal limb ischemia, where the same concept focused on creating control levels of stenosis to restrict flow and study its impact on distal perfusion. To achieve this, we developed a 3-part femoral artery mold with an interchangeable core, allowing us to modify the inner diameter and test different levels of stenosis. To achieve our final design, we evaluated 3 design concepts that, and by doing these evaluations, we thought that we needed to consider the length to be able to properly visualize flow and cannula behavior. We needed to reduce complexity of the geometry of the system, and we needed to be able to change the diameter to simulate different levels of stenosis. This led us to choose our design concept 3, which allowed us to properly visualize the flow and the cannula behavior, to change the core diameter to simulate different levels of stenosis, and it showed a stable and reliability during testing. Here is a demonstration of our stenosis artery where we injected a red dye, and as we can see, there is red dye going into the proximal direction to the right, but there is no dye going into the left, showing that our stenosis artery successfully occluded, replicating distal limb ischemia. Now Alejandra is going to continue with our last requirement.
Thank you, Oscar. For our last requirement, we needed to be able to enable a control system for our ECMO model. To do this, our design inputs were to include both flow sensors and pressure sensors, as well as a controllable pump model. On this slide, you can see our electrical architecture. It's made of 3 main components: an Arduino Uno, a motor driver model L298, and a 12-volt power supply. On this next slide, you can see a graphical user interface that we use Python to develop. In here, you can connect the system, set the desired flow rate, run and stop the system. I would like to mention that every time a system run is completed, an Excel document is automatically saved to all the information collected. Here on the right, you can see the live telemetry that we're able to see every time we run the system, and that way we can keep track of the flow and the pressure. Next, I'm going to pass it back to Oscar to discuss the verification.
Thank you. To confirm our control system, we needed to confirm 3 things: flow control, flow sensor accuracy, and pressure reliability in our system. Now we're going to show you the results for the validation of this. Here we can see a plot where we can see that as PWM increases, the flow increases as well linearly. The R squared close to 1 shows that this relationship is highly predictable, and this allowed us to obtain the values that we needed that are 4 to 6 liters per minute. Next, for flow accuracy, we compared the flow sensor readings to collected volume. And as we can see, the error for water and blood analog is very small, showing the accuracy of our flow sensors. Lastly here, we show different values of pressure that we adjusted with our needle bulbs. And as we can see, these values fall within the range that we need of 0.77 and 2.20 psi. So putting all this together, we were able to successfully complete our three main objectives. We built an ECMO flow loop with replicated thermal stenosis, and we assessed a control system to monitor and control pressure and flow. Now Alejandra is going to continue with the impact of our project.
Thank you again, Oscar. For the impact of our project, the main point would be manufacturing. We were able to manufacture our device for under $550, and we were able to do this by using readily available components and also did the entire assembly in-house. For the financial side, we focused on the future cannula that is going to be developed, and this landed us in a $150 to $300 million market. Now I'm going to pass it on to Rachel to discuss the global impacts.
Thank you, Alejandra. Globally, an estimated 27,000 to 46,000 patients that are placed under ECMO develop dystolemia ischemia each year, highlighting the scale of this problem. In order to combat this, we are going to reduce these complications and in turn reduce healthcare costs and improve patient outcomes. And in addition, by improving the cannula design, we are also supporting more consistent testing worldwide. So in order to bring a future ECMO cannula into the market, it would be classified as a Class 2 FDA device requiring 510K pathway clearance, meaning it must demonstrate safety and performance through established testing. These standards, some of the standards that we covered were ISO 10555 for intravascular devices, along with ISO 10993 for biocompatibility. Other sterilization standards were also considered for clinical use. We have here our market gap. So the ECMO market right now it is established, but it's not necessarily overcrowded. Most of the designs that we have are simply iterations, not breakthroughs, and this is exactly what opens the pathway to create a bidirectional cannula that is able to provide that distal perfusion without requiring any additional add-ons. So for the future work of our project, we plan to incorporate more realism through pressure regulation throughout the system, along with enhancing the elasticity materials to have more realistic accuracy, along with the incorporation of a centrifugal pump. And we developed some ANSYS simulations here in order to demonstrate healthy and stenosis arteries. The open artery simulation shows smooth patterns of flow, whereas over here the stenosis artery shows flow disturbance and disruption. So, in order to summarize, femoral cannulation leads to distal limb ischemia and limb loss. In order to address this, we created an ECMO benchtop model that is able to accurately and replicate controlled flow and pressure. This is able to open the future for the bidirectional flow cannula. We would like to thank our mentors and our advisors, along with the department and everyone who was able to make this possible. Thank you guys for taking your time to listen to our project and our presentation.
Judges, feel free to take a closer look if you are so inclined. Please.
Just a little confused in the last part where the device was classified as a Class 2 device. Are you guys, the design here, is it the phantom or the actual connection?
That's a great question. There is a bit of confusion with that because our device is a research and development device. This is not going to be brought to market. This is for our sponsor to use to develop a cannula that will in the future be classified as a Class 2 medical device. This itself is not subject to FDA scaling regulation.
What were some of your challenges through the integration of this?
I think I'll actually hand it off to Alejandra to talk about some challenges specifically with the femoral artery module.
Thank you for your question. We have many challenges, as I feel like all of us did. This was a very steep learning curve. The first challenge we had was we have 7 different iterations of the femoral artery module. We kept iterating new ones because we kept having issues with the molds sticking to the silicone. and every time we would try to demold it, it would stick. So it was a long process. It was very labor intensive. I think this was, in fact, our biggest challenge with this project. Anything you'd like to add?
Well, initially we had trouble finding what was the tubing size that we needed to properly simulate this. We started with 1/4 inch, and then we went to 1/2 inch, and that allows us to basically recognize which will be our failure point, which is when the system is at 5 psi. It's when we start leaking, and that's basically our failure point with pressure.
Any more questions?
So was that your only FMEA, or do you have any other failure modes that you have assessed for this?
Well, I think one of the biggest failure modes that we had was whether or not we would successfully be able to recreate occlusion in the femoral artery, where that is, if that doesn't work, and we aren't able to restrict distal flow with a typical cannula that you can buy on the market, which we have, that would be the point of failure, that the project just doesn't work. But we were able to recreate that. We were able to create a stenosis type artery, which was passed around, and I'm sure as you guys felt, it was very stiff in the middle, and then we had the non-stenos that allowed for both proximal and distal blood flow, replicating a healthy artery.
What was the sample size that you guys conducted for your verification tests, and what drove that sample number?
What specific sample?
Of testing, how many tests did you do?
Well, for example, for the flow, we ran 10, I think we ran from 60 PWM to 135. So that's in increments of 10.
Yeah, so for that flow, for the test that Oscar was talking about right now, which was our verification that we were able to properly control flow with pulse width modulation, we ended up running 13 trials for that verification test. We did 13 trials for a stenosed artery, 13 trials for a non-stenosed artery, we did 13 trials for water, 13 trials for blood analog. So it's all interspersed through there. When it came to our sensor verification program. Oh, Y13. It was so that we could test and try and find the numbers that get us through that operating range of femoral arterial ECMO.
4 to 6 liters per minute.
So we were trying to go through there and then verify that we are able to control it repeatedly.
Okay. Thank you very much. Team number 7. And I now call team number 8, state team number 8. While we afford the judges a few minutes to gather their notes. Team number 8. Sponsored by Expo Medical. Restore. Reduced effort system for tibia orthopedic removal and extraction. The faculty mentor is Dr. Shulang Zhao, and the alumni mentor is Mr. Richard King. It says here the project manager is Miss Janella Esquizel. Other team members, Evan Gonzalez, Moshe Hurakan, and Jacob Mata. Please
Hello everybody, we are FIU BME Senior Design Team 8. My name is Jacob Mata. We have Janelle Esquivel, Moshe Wako, and Evan Gonzalez. And our project is Restore, a reduced effort system for tibial orthopedic removal and extraction. Our sponsor company is Expo Medical, a leading orthopedic extraction company coming from St. Petersburg, Florida. So every year, tibial fractures are the most common long bone fractures. Specifically, tibial shaft fractures happen in the US around 50,000 times, and if we look at globally, it happens well over 1 million times. And so to help facilitate healing of a tibial shaft fracture, an intermedullary nail is put through the axial direction of the bone, and after successful healing, the patient may require it to be removed due to pain, discomfort, or further surgery of the area. And so currently, to remove the intermedullary nail, surgeons use very barbaric methods of swinging a mallet at a C-frame as one of the options to draw the nail out. And so this is very effective, however, it uses a lot of surgeon effort. The surgeon has to put in all the effort to do it. And another method is a slap hammer, and this is even less effective, and they have to put in even more effort, and it moves the nail even less. So surgeons are using a lot of force, and this is a problem because 97% of orthopedic surgeons nowadays in their career report musculoskeletal disorders and diseases and injuries, and 20% of these surgeons need a surgery for themselves. And the American Academy of Orthopedic Surgeons have reported that by 2050, all orthopedic surgeons are going to have to increase their workload 50% to meet needs. And to make matters even worse, this doesn't just affect the surgeon, this can also affect the patient. Since they're swinging these mallets, if they're uncontrolled, if there's too much force put on the bone or surrounding tissue, it can cause tissue damage or even refracture the bone itself. The cortical bone of the tibia breaks around 85 megapascals, so once again, if it goes over that, the bone will break. So this isn't just a problem in the hospitals, it's also an open market. So globally, the intermedullary nail market is projected to grow from $550 million in 2025 all the way up to $850 million by the year 2035. Now in North America, the orthopedic power tool market is expected to grow 9.36%, and specifically for extraction, it's supposed to grow 19.78 million% within the next 5 years. So, and the North American intermedullary nail market related to tibial extraction within the next 5 years is expected to grow 11.62 million%. So there is a clear need for a device that removes the intermedullary nail from the tibia but doesn't put all the effort solely on the surgeon. That's where we introduce Restore. Janelle will talk more about our device.
Thank you, Jacob. Restore was designed to overcome these limitations of the current manual tools, and we aim to save the patient and save the surgeon. Now, I would like to present Dr. Osorio, a Peruvian orthopedic surgeon, who will talk about the global perspective of current manual tools and the future of Restore. She's talking in Spanish, by the way, so it still has subtitles. Thank you, Dr. Osorio. Now,
cirujano y el riesgo sobre la porción cortical ósea.
okay, thank you, Dr. Osorio. So now, I would like to talk about Restore. Restore highlights 4 key features: rapid release, high energy, ergonomics, and a control system. This device works by providing a force and so compressing the springs right there, and then being controlled by the arrow, as you can see in this picture. Then to accomplish these features, we created first our engineering marker requirements, and then we developed our design inputs. First, we have one of our main design inputs, which was to accomplish more than 30 joules per strike. And then another one was to not get into the maximum limited stress of 85 megapascals to not break the bone, of course. Now, to build on this, we have another critical engineering marker requirement in the design input that was that the device was accomplished more than 350 millimeters along the longitudinal axis, which was the total length of the IM nail, the one that is inside that bone. Then we created this design progression, our 3 main design concepts.
We first started with a spring gearbox mechanism, which was an efficient energy storage. However, it provided an inconsistent impact energy. Then we continued with our screw ball mechanism, which provided then our linear actuation and a linear impact. However, it provided a low impact energy because it was to control. Then we have our third design concept, which was the one that was a must control, and it also attaches to the extract hole, universal extract hole for orthopedic surgeries. Then we had a cons, which was that it required a CAN design, but we achieved this by creating this wire right here with the exact segment with 80 millimeters. This MVP was divided in 3 main subsystems. We have the electrical subsystem, we have the mechanical subsystem, and the housing, which will house and enclose all these 2 subsystems. The electrical subsystem was divided into the motor driver, the motor, we have the microcontroller, and all was powered inside there by the batteries. Then we have a mechanical subsystem. This was right here. The top wall was one of our main components being extracted by the slider and being controlled by the cane barrels, as you saw before in the video. Now we will continue with Moshe simulations.
Thank you, Janelle. As you can see here, we have our critical components, which are the mechanical assembly. We had run the simulations in order to assess if there's any static displacement or any bond misses. We ran simulation for bond misses stress. We ran it for the threaded bars and the top wall. As you can see, the threaded bars are one of the main components because the load path is going through that component. And the top wall is the one that is receiving the impact itself. We had other simulations for the mechanical portion of the movement. Here we have the slider, which is actually delivering the impact. And we also have the camping, which is going through the path of the barrel as the barrel is twisting because of what the motor is providing. Then we have the middle wall, which is another critical component, and the strut belt that you guys had going through there, which will actually attach to the bone and will be the interface for our device. We also ran battery simulations in order to have that. Even if the battery is fully charged or lower charged, it will give us the power needed, and all of our electrical components will be safe enough to deliver the energy required. As well as the manufacturing, we use all steel parts that are used already in the surgical OR, and our team assembled the mechanical portion, the circuitry, and as well as the programming in order to turn the motor on and start the mechanism. As for the testing, we have battery testing verification, which allowed us to see that it will last more than 100 cycles. The weight verification, so that it's less than 8 kilograms, so that it's ergonomic and comfortable to use. The ion nail traction verification, which was bench testing, and allowed us to see the movement of the actual ion nail. And energy verification, that was through the difference in position in the y-axis and difference in time, so that we can have the velocity and so we can calculate the energy. As for the raw data, we had that tracker motion for the position and the difference in time for the slider and for the ion nail extraction of the whole assembly and device testing. You can see the raw data here. And for the stress and force data, we actually had a load cell that gave us the force in units so that we can calculate the stress. And then you can see it's well below 85 megapascals. For the statistics,
Thank you, Moshe. So now, going on to the statistics. So for our first verification here for our critical DI and making sure that we could output the greater than or equal to 43 joules per strike, we have the motion analysis data right here. We did 10 trials. After doing all those velocities from each trial, we calculated an average velocity, and from there, use that to calculate the energy, as you can see right there. Then moving on to the next one. The next one was using a load cell. We did 10 trials as well, getting the forces from those 10 trials. So make sure that with that and the contacting surface area to see if the stress was lower than the 85 megapascals, which we achieved. Moving on to the next one. So this DI was to make sure that we could achieve extracting the nail as a whole. And as you can see right here with the 10 trials, we succeeded in approaching that limit that we were looking for, as well as on the trial over here, making sure that with a 0.35 millimeters per joule per impact, which is 1 impact per second,
we got the efficiency from the displacement over the total energy, and as you can see, even our lowest one, which was 0.36, was still over the 0.35 that we were aiming for. Then when it came for the statistics as a whole for all 4 of these, we did t-test, just to make sure that we are comparing it with a 95% confidence interval to succeed in doing this. All 4 of them did pass, as you can see here. So our device Restore succeeded in delivering efficient force output and reducing surgeon effort. On top of that, we succeeded in attaching to a universal attachment, which we had passed around earlier, which our company Shupa does provide for us. And on top of that, reducing the surgeon fatigue. Our budget was that we were allocated was $8,000, and we succeeded in delivering lower than that and not going over budget, as well as our unit cost for the device is going to be $15,000. Now, for the future work, our global implementation, we do want to make this device more accessibly globally, especially when it comes to different countries that may not be able to afford the resources that we have here in the US. Then, as well as doing OR trials for the validation, reducing the noise, and then finally, and further reducing the surgeon fatigue, possibly doing a stand later on. Then for intellectual property, as you can see right here in this image, it is a bidirectional impactor for orthopedic intramedullary nails. However, it is currently not on the market, and the patent is on the structure itself of the device, not on the functionality of the device. So our device is still a novel device that has the ability to be patented. And here are our regulatory assessment and the standards that we have. Some of the critical standards that we do have are the risk management when dealing with the electrical components, as well as the biocompatibility. And our device is a Class 1 device. Here are our references, and now we would like to offer a special thanks to our sponsor, Shupa Medical, as well as Dr. Christie, Professor Sherislani, our faculty advisor, Dr. Zhao, our alumni mentor, which was Richard King, and all the DME faculty and staff that are here, as well as everybody here in the panel as well. Thank you, and I would like to open up the floor.
Thank you guys so much for the very nice presentation. I wanted to ask you, when it comes to noise, how do you plan to reduce the noise? What's the idea for future improvement?
Yeah, so this, the orthopedics OR is usually not it's not a quiet place when it comes to these procedures. So thankfully, since this is in, in a container that's going to be sterilizable, we will be able to put some type of insulation in the future to reduce the noise. Compared to, in the videos, in the current modality video, the audio is loud, it was extremely loud. But our device isn't as loud as that, thankfully, and it's due to that box, but, by putting further insulation, it would be able to drown out the noise even more. You got a question for me?
Thank you guys. Really cool project and great presentation. So I think everyone's aware it's a little heavy, understandably so. So I'm curious how you determined the 8-kilogram limit for the weight design input. And then also, how long would you expect the surgeon to have to hold this up? Like, how long does it take to actually extract the nail?
Okay, so yeah, we decided on the 8 kilograms because it was, when we originally set out to make this out of stainless steel, we realized that stainless steel 17.4 pH is very wear resistant when it comes to high impact. But once again, it's not a light material, so we decided that 8 kilograms. So to answer your question about how long it's going to hold, with our device, with the amount of joules that it's putting, it should take about 20 hits, and at 1 hit per second, it'll take around 20 seconds. So there's no time on how long it actually takes. Like currently with current methods, there's reports of it taking, sometimes even an hour to get it out. But so it should take 20 seconds. So it shouldn't be, it wouldn't be too long. So most surgeons will be able to do it. I think most people want to do it.
Yes, so like 8
Yeah, for the 8 kilograms, it was more about we knew kind of through research and literature that there's a wrist torque limit in the wrist. So it has like 14 Nm. Therefore, for each wrist, we kind of had just a little bit below that. That's
Good job, team. As far as the angle that they have to hold it at as well, did you guys consider that? Because not only is it heavy, it is the angle that they have to hold it at. You got 20 seconds.
So thank you for the question. So when it comes to the angle right now is typically around 90 degrees to 45 degrees, depending on how the surgeon prefers it. Now, based off of the angles, we took that into account just because the surgeon likes to, based off of the ergonomics and through research, we saw that those angles allow the best ergonomics in doing those different angles, especially when dealing with that weight, especially as my colleague Moshe had said previously, the 14 millimeters on the wrist torque, and just making sure that it doesn't go over that specifically.
Yeah, so there's also 3 types of kind of methods to extract the IM nail. So either it's by 90 degrees, so right here, you can extract it like this. The patient will be sat down and they have their knee like this, so it would just go straight. There's a 45-degree angle, so the device will be held like this. And then there's, if you turn it around, it would actually be one of the methods here that's up here shown. Just put it 90 degrees. It would actually be extracted this way, so everything is like just vertically. So it would be held comfortably here at this angle for the surgeon.
So it kind of goes with the weight, and did you guys test if it passes dropping it on the floor? If when a surgeon accidentally drops it as he gets fatigued and he actually drops it on the patient or on the floor, how does this resist to that force?
Thank you for that question. So everything right here is connected through the thread bars. So as you can see here, so everything right here is connected to the thread bars. Everything right in the all the mechanical components right here, the barrel, the slider, and the top wall, it's connected together. Even if it drops, it will not move at all. And then we have all the electrical components right here. It's all assembled together and it's connected and it's already, this soldered. So it will move even if we put it to the side, if we lay it down or anything. It's all already assembled as it is, and it will move. Like we already tried moving it around and it will move. We open it again and we close it again. It takes a while, but of course, the only thing that the surgeon has to do is only click one of those 2 buttons and it works. That's how we can show right now. Yeah, we can show right now.
For your answer, we did not test for drop testing, but that will be one of our improvements for sure. It is stainless steel, all of the parts. So if there are threaded parts, they're all bolted together. So we believe we made a very sturdy design.
I just had a quick question when it comes to reducing fatigue. Were you guys able to test it in some phantom bone grafts with doctors? Because you claim that that's one of your proposals. How did you guys verify or validate that that actually happens? Because through the video, it only takes 30 seconds to take that part out. It goes from an average from 30 to 2 minutes, depending on how complex it is. It can obviously extend. But ultimately, how did you guys verify that you guys are actually reducing fatigue?
So thank you again for the question. So when it came to verifying the reducing of fatigue, we based it more off of just the weight itself, especially because on that amount of 8 kilograms, that was a weight that with the wrist torque, it's not really putting a lot of strain still on the surgeon. It still is some strain, but still bearable strain, especially after we consulted with the orthopedic surgeon that we had, talking to her about it. She said that that should be enough strain that she should be able to deal with it, especially because typically right now, how we had said previously, these surgeries are not, there's no standardization in the time. So right now it could take 2 minutes or it could go all the way up to an hour or more. So she said, especially if it's that time, the less amount of time, she should be able to do it. And then of course, she did say to us, like for future reference, especially in the future works, if there's some way or another of putting a stand or anything like that to further reduce it even more, that she only has to just hold it just to guide it in the end, just to make it even easier for her. She actually really liked that idea, and we plan on doing that later on as well.
Thank you, Evan. Just to add on to that, the poi synthesis has an orthopedic hammer, but it's for total hip arthroplasty, and it's set out to do the exact same thing, and they proved to do that. They did the EMG testing with surgeons, so that would be a future work for us, is when it's in clinical trials and operating rooms, we can test with surgeons to confirm that it does reduce. Any other questions? Thank you again, guys.
Okay, thank you so much. Last question, or maybe more.
So do you expect that there'll be like zero damage to surrounding tissue with your device?
Thank you. Yes, so we're expecting to, of course, accomplish less than the 85 megapascals. We actually, after accomplishing the force, which was 9 kilonewtons in the device, not at the bone, it was good enough to not be like, not even 10 megapascals, so you're pretty good in like not making any breaks in the bone or anything. So we are good at that point, even though it was high force, it's proven that it won't break or unalign the axis of the iron nail with the device.
That's it.
Thank you, it was a pleasure.
Thank you very much. And so judges will retreat to the BME conference room. Audience, after the congratulatory messages, I invite you to join us at the Panther Pit for the Junior Design Poster Competition, which will immediately be followed by a lunch session. So take it away, sir.